Okay, well, I trust everybody had a good spring break.
Yeah.
Good.
Too short.
Too short. It's always too short, just like the weekend, right?
Yeah.
The problem with spring break is you think, oh man, I've got all the rest of this time to do this. And then the second day you think, oh man, I still got those. And then by the time the weekend rolls around, before you know it, it's all gone. Anyway.
Hey, what?
We did have there is a homework assignment due today. Oh, which assignment? A12, is that what it is? Yeah, it's assignment A12. And I think this one,
Yeah, the chart.
yeah, I want to actually do one of these for you to get you started, to show you how we, yeah, we'll do
that right now.
Well, I mean, there were 3 proofs, right?
Yeah, B, C, and D.
B, C, and D. And here, let's take a look at this, at our table 14.1. It's just to show that the property is equivalent to the alternative. So it's these are all equivalent theorems, right? And I think in class last time we proved A, right? That a property was equal to its alternative. So are there any questions about those other 3 ones? I think they're pretty straightforward.
I have a question on the other one.
Yeah, okay. So now the other one, so let's talk about the other one. The other one is exercise 14.27. So this is 14.27. And because it's an exercise, we won't put a parentheses around it. And here's what you should do with 14.27. The solution to 14.27 should be in the shape of a table. And the table should look like this. Now, which parts were assigned? Wasn't it like A, B, D? Okay, so put A, B, D. What was the other one? F, G, H, I. Like this, right? And then across the top, put reflexive, these properties from here. So reflexive, irreflexive. Okay, so this table has 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 6 times 7 is 4. So there's 42 answers. In each one of these things, you have to put a yes or a no. All right? Now, so what is it asking? What is the question asking? Well, each one of these letters, it is defining, the book is defining a relation. It's giving the definition of a relation. And then what we're asking here is that relation reflexive? Is that relation irreflexive? Is that relation symmetric? Is it antisymmetric? Is it asymmetric? Is it transitive? So you put a Y or an N for yes or no, depending on whether it satisfies each one of those. So as an example, I'll just give you, we'll just do A, right? Part A of this, for this. And what does part A say? Part A defines what rho is. It says B rho C if and only if B and C are both positive or both negative for integers B, C. So I think what we should do is do a few examples of ordered pairs. So what ordered pairs are in the relation rho as defined for part A of this? It says it could be -2, -2, -2, -1, -1, -2, -1, -1. Now, and then a bunch more before that, right? And how about 0, 0? Well, see, 0 is neither positive nor negative. So 0, 0 is not in there, right? So another one it could be 1, 1. It could be 1, 2. Could be 2, 1. Could be 2, 2. And an infinite number more in that direction, right? So does everybody understand that these are the ordered pairs that are in this relation rho as defined by part A of exercise 14.27? Are you with me here? Okay, so now what we have to do is we have to figure out, is this relation reflexive? Well, what does it mean to be reflexive? What does it say up there on table 14.1? What does it mean to be reflexive?
Rho B, B rho B.
So is it true that for all B, B rho B, well, we've got -2, -2. We've got -1, -1. We've got 1, 1. We've got 2, 2. But we don't have 0. So this is no.
So even though not all of them are reflective?
It says, in order for the relation to be reflexive, for all B, so that includes 0, but 0, 0 is not in there.
But it doesn't matter if you have 1 and 2 in there?
It doesn't, yeah, good point. That's irrelevant.
We have all but 1. That's not all.
But no, she's asking a different question. She's saying, but what about the fact that it's not only those, it's that for all B, B rho B.
So isn't it no because there is a 2 and a 1 together?
No, 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 no. If, that's not quite right. If in fact we had another relation, call it sigma, and it was the same as this, but in addition it had 0, 0,
Yeah.
that sigma would be reflexive, even though it had these other ones in it. That was your question, right?
Yeah.
All right. Is everybody with me on this?
Wait, so what if it was just 0, 0?
Yeah.
Well, if it was just 0, 0, it would depend on if it was over B. I mean, it would depend, if it was over all the integers,
Okay, so if the
it would not be, because 1, 1 would not be in there.
Depends on the range, yeah.
Yeah, well, it depends on the set over which it's defined. Okay, we're assuming this is over Z cross Z. It didn't say otherwise, right?
It says for both integers.
Oh yeah, are both positive or both negative for integers. Oh yeah, it did say. It said for integers. So we are assuming that this is over Z cross Z. You know, is the. Okay, does everybody see then why? Okay, now let's see if it's irreflexive. Let's see if it's irreflexive. What does it mean for irreflexive?
Rho B, not B rho B. That means there isn't a single reflexive element in it, right?
Correct.
Which there is.
Hmm?
Which we do have 2, 2 or 1, 1.
Yeah, yeah, yeah. So therefore, irreflexive was what?
No.
No. Okay. Does everybody understand how to, what we're doing here? Okay, now what about symmetric? What does it mean to be? That means B rho C equivales C rho B. That means if you have ordered pair BC, you have to have ordered pair CB, and the other way around,
I think we have that.
And if you don't have the one, you don't have the other. So is it symmetric? It is. I mean, if there's a -2, -1, there's a -1, -2. And if there's not a 2, -1, there's not a -1, 2. See? And there isn't. So it is definitely symmetric. Okay? Now okay. And then how about antisymmetric? What do you think about antisymmetric? What does that say?
If you have B rho
Well,
C
C-
and C rho B, then you have to have B, or then B equals C.
Then B equals C. Well, what do you think? Is it antisymmetric?
No.
Why not?
because of -2, -1, -1, -2, or 1, 2, and 2, 1.
Yeah, yeah. You have -2 rho -1, and you have negative. We have -2 rho -1, and we have -1 rho -2, and -1 is not equal to -2. So antisymmetric is what? Niet.
It's neither asymmetric.
Yeah. What about asymmetric? Well, let me see. That was antisymmetric. Yeah. What about asymmetric? Now, why isn't that?
Because it's symmetric, really.
You better not go down that road. But anyway, what is it? B rho C implies not C rho B.
If you have
But we have -1, -2. We don't have, yeah, so this is no. All right. And then what about transitive? If we have if we have B rho C and we have C rho D, in other words, if B and C have the same sign, are you with me?
I think yes.
If B and C have the same sign, because that's what it means to be in there, right? And C and D have the same sign, does it imply that B and D have the same sign?
Does
The answer is yes.
does the relation, do we have like -1, -3, or -1, -4?
Yeah. This is dot, dot, dot.
Okay.
This is dot, dot, dot. So I didn't do all of them. I didn't have an infinite number of
They don't
space.
have to be just one apart, right? Okay.
Correct. Yeah. Oh, I see. Yeah. There's a -3, -1 also, for example. All right? So then they give you these definitions. So here this defines a different row. So what I recommend you do for this one is you write down a few samples. You write down a few examples like we did here, because it kind of helps you to visualize and see where, see what those are, and then work through all that. So it's a big exercise on how to. And then the other thing, here's another thing. I have a few extras of these, so I don't think everyone got everyone. This is homework for due today. But I handed out this sheet last time. You can download it from the website. But it's called Visualizing Relations. Did everybody get one of these?
It wasn't on the website.
Oh, it wasn't? I thought I put it up there. I think I might have put it up there later. You might want to refresh your browser. But and this visualizing relation, we introduced the concept of last time, or maybe the time before, of how to represent this with a graph, but then we also showed how to represent it with a matrix. Remember, and it was a matrix of ones and zeros, and if it was row I, column J, had a 1 in it, then that meant ordered pair IJ was in the relation. And so this, I think if you as you're doing this, I think if you look at this and try to visualize what the matrix looks like, this is another way of learning the meaning of each one of these properties of relations. And also, I think the other thing that I think will help is if you look at the alternative definition. That alternative definition, you can picture it you can picture this as a matrix. So I sub B, for example, the reflexive property, using the property directly, it's for all B, range true, B rho B. But the alternative definition is I sub B is a subset of rho. Well, what is I sub B? That's the identity matrix. Well, look at the identity. Here, the identity matrix is, the identity relation is here. It's near the top. It's the third matrix down. That's the picture of the identity relation, yeah? It's ones on the diagonals and 0 everywhere else. So if you just imagine it as a matrix, you can say, oh, well, are ones on the diagonal? If ones are on the diagonal, it's reflexive. It's if if ones are on the diagonal. Yeah, that's right. It is right. So if ones are on the diagonal, it's it's another way of visualizing, I think, that might be helpful. Okay, so
What does it mean to be a parent?
That's a good question. That's number.
I tried to look in the book, but
Yeah, no. This is not a mathematical thing. This is the father of. This is human relations. This is family relations, right? No, it's a relation, right? Aren't you related to your father?
I hope so.
Well, so if A, look at if is B rho B, is B the father of B?
No.
Well, so it's not reflexive.
That's so silly.
I know, but which one of these, the father? That's literally.
so is
trivially
B the father of D then? Or is it only
No. It says B. It says for all people,
It is transitive.
B is the father of B. It is transitive.
Isn't it?
Well, you think about that. You think, and I'm not going to say
Wait,
you.
so anyone that's higher up is
It-
the
Oh,
father
that'd be
of
good.
No. We're talking about families,
Yeah.
and those are people. For all B, for all people.
Yeah.
So is it, if it,
We're talking about, we're talking about people here.
So would it be transitive? 'Cause because if he's the father of someone else.
Well, look, if B is the father of C and C is the father of D, does it imply that B is the father of D? This is a father of.
Yeah.
It's grandfather.
So does
Well-
grandfather count?
No, it doesn't, so it's wrong, it's false.
Well, you put Y or N here, depending on whether you think if, you know.
Right.
So anyway, you just think about, I mean, this works. I mean, that's a family relation, right? That's why we call them relations. I mean, these are relations.
It is anti-symmetric, isn't it?
Well, I don't know. Think about it. We won't do the homework here.
Wait, can we do 1425 though, that first one?
What?
1425.
What, you mean proving?
Are we going to do it?
No, that's a homework
See what
problem.
we're going to do.
No, I said that's a homework problem. We did A. You're going to do B, C, and D for me. Right?
I'm lost. I'm stuck.
Well,
You just want
think about it.
You just want it to look like that.
No, wait. I thought you were talking about
He's talking about
the previous one, the proving.
Yeah.
Yeah, no. We did A in class. It's your job to do B, C, and D.
Can I have a hint?
Well,
I'm stuck.
well,
Start with the right hand side, I know that much.
yeah, exactly. I think all of these, it's good to start with the right-hand side. So what do we have here? Equals, so, yeah, what does it mean? I sub B intersection rho equals the empty set. Yeah, use 1148. But it's the, it's with two variables for all x, y. Yeah, that was a good.
Oh, actually, I had a question on that one. Because it's not an element of P. How do you make that the not, like the different not? Can you just say it by definition of?
No, not means, just carry through the not is an element of, and in the end, you know the notation. That's yeah. Actually, you're using 1415.4. This. Yeah, not is not out in front. Well, yeah. Actually, here we would go all the way back. Here, we'll do it.
It's like the meta theorem.
Yeah. No. Hold on. Oh, we don't have it down here. There's a footnote here on your equation sheet that says if there's a slash between it, it means not out in front. Okay, remember that? Okay, now last time we talked about the concept of closure, and I just wanted to do a couple more examples of closure before we move on to equivalence relations. So, do you remember the idea of closure? Gee, that was such a long time ago. That was before spring break. You remember you had to add, how many different closures are there?
What's a closure?
Shoot, we did this last time.
Long time.
Yeah, it was a long time ago. Do you remember what a close, what it means to close a relation?
Just
Oh, isn't it kind of like a compliment?
No,
It's like everything else.
no.
It's,
Remember the idea? There was an idea.
it's like what the set means
To have a property, yes.
Yeah.
It's like, what do you have to add to the relation to give it a property that it doesn't have yet? Do you remember that?
Like we could have added 0, 0 to the left.
Exactly. We could have made, that would have been the reflexive closure. Ooh, what a great example. Oh, good call. Yeah. Yeah. If we'd added a 0, 0, that would have made it, that would have been the reflexive closure of that relation. So how many different closures do we have here?
Lots.
No, I mean how many different types?
3.
3. We've got here, it says, what's it defining? The reflexive closure,
Subset.
the symmetric closure, and the transitive closure. Remember, those are the 3 kinds of closures that are possible when we read this. There's a reflexive closure, a symmetric closure, and a transitive closure, right? And so he didn't want to do 14.30 with just the word reflexive in it. If he had done 14.31, he could have done the same thing, and it would have been, everywhere there's a reflexive, he'd say symmetric, and then he could have done a 14.32. And everywhere that's reflexive, we would have said transitive. So this is actually 3, you get 3 for the price of 1. 3 definitions for the price of 1. So there, remember we had a little chart up here. There is a reflexive closure, a symmetric closure, and a transitive closure. And what does it mean to close a relation? What do you do to it? you add ordered pairs to it, but now to give it that property, but only the ones that you need. No more. Do you remember that? So and then we went through it in detail. We went through an example of C. If rho prime prime is reflexive and rho is a subset of rho prime prime, then the true reflexive closure, rho prime, has to be a subset of rho prime prime. So rho prime prime would be something that you would get by adding more than enough. But the true reflexive one has to be a subset of that, of any one that is reflexive. Okay? Now, so let's do some examples. Oh, and here's some notation. I'm not going to dwell too much on the notation. Well, R sub rho is the reflexive closure of rho. S of rho is the symmetric closure. Rho plus is the transitive closure. And rho star, now here's the thing about this. This actually has application in compiler construction theory. Rho star is the reflexive transitive closure of rho. Okay, so that's just some notation stuff. And 14.31, it's kind of trivial. If the relation is already reflexive, then that is the closure. That is the reflexive closure. In other words, you don't have to add anything. So you're just okay. And a symmetric relation is its own symmetric closure, and a transitive relation is its own transitive closure. So those are trivial. Okay. Now, so let me do an example of 14.2. 14.2 says let rho be a relation on a set. Then the reflexive closure of rho. What do you have to do to make it reflexive? You have to add what?
Something to make it reflexive.
Yeah, and what kind of things do you add to it?
Ordered pairs.
Ordered pairs, and what do the ordered pairs look like in order to be reflexive?
They're the same.
Yeah, BB, you know, yeah, like they have to be the 0, 0, 1, 1, 2, 2 if they're integers. They have to be the same, so you add BB. So what does this say? So what does this say you have to do? You union the identity relation. Okay? So let's do an example. Here, let's do 14.32. Well, the example of that one is like the one you pointed out where we added 0, 0 to that other one. Let's do B. 14.32. Ooh, this is a weak pen. It needs to be consigned. Watch out. Oh. That's better. Example of what is symmetric closure? So let me just make up a short example. Suppose that we have B, the set is 0, 1, 2. Okay, and let's just take a look at the less than relation. So what's the less than relation over 0, 1, 2?
0, 1, 0, 2, 1, 2.
All right.
0, 1, 0, 2, 1, 2. Okay, and now what is the symmetric closure? See, it's S. The symmetric closure. So what do we have to do? So what does this say we have to do with this? We have to union this set with this set of ordered pairs with what set of ordered pairs?
Greater than?
Hmm?
Because if there's 0, 1, there has to be a 1, 0, right?
Yes. So what is rho inverse? Rho inverse is the set of ordered pairs with them switched.
Right.
Okay, so we have to union this one with the set that has them all switched. So what would that be?
So it just needs
0, 1.
all those.
Yeah, you always have to start off with your original.
And then 1, 0, 2, 0, and 2, 1.
And then, yes, and then you've got to have 1, 0, 2, 0, and 2, 1. All right? Does everybody see how that works? Okay, so I think there's some exercises for you to do, some closures next time. And now let's do, this one's a little trickier. C, example of transitive closure. So let's do this one. For this one, we're going to use that pred relation that we had before. So let's say B is the set of elements 0, 1, 2, 3, and let's call pred the relation, the immediate predecessor. So this would be, remember how that worked? 0, 1, 1, 2, 2, 3. Okay? And now what we want is we want the transitive closure. So this would be pred, the notation for that, it's pred plus. You put a superscript plus. Superscript plus, that's the notation for the transitive closure of Rho. Okay?
So we need those original ones.
So we need these original ones, but now this is tricky, you guys. This is 0, 1, 1, 2, and 2, 3.
And then we need
But-
0, 2, 0, 3, and 1, 3.
Yeah, well, now what, yeah, that's, yeah. So what we have to look at is we have to look at all of these, and we have to see that wherever there is, if we have to search for a 0, 1, and then a 1, 2. Well, if we have a 0, 1 and a 1, 2, in order for it to be transitive, we have to have a what? A 0, 2. So this would be 0, 2. Are you with me? Okay, but we have a 0, 1 and a 1, 2. We got okay, but we have a 1, 2, and we also have a what? 2, 3. So we have to have a what? A 1, 3. But look, now notice that I put these on this line and I put these on this line. These on this line are obtained by trying all the pairs of these to see if there is an AB and a BC, right? And if AC isn't in there, you add it. But just because you've done that with these three to get this, you're not done. So now what you have to do is you have to look at all of these. Are you with me?
Yeah.
And see if there is a...
More transitive.
Yeah, more trade. So here we have a 0, 1 and a what?
A 1, 3.
1, 3.
Oh yeah, a 0, 1 and a 1, 3. So we must also have a what?
0.
A 0, 3.
Now we're done.
Now are we done?
We could have looked at a different example
We
for
could
that.
have done 0, 2, 2, 3, but we have 0, 3.
Yeah. Now the way to visualize this for transitive, I think a neat way to visualize this is to use the graph representation. So the original representation looked like this: 0, 1, 2, 3. Now originally, remember that it looks like this. Our original one looked like this. There was a 0, 1. There was a 1, 2, and there was a 2, 3. So we have an arrow going from 0 to 1. We have an arrow going from 1 to 2, and we have an arrow going from 2 to 3, right? But then what happens is, because you can kind of see, oh, look, I can get from here to here from here. So therefore, I have to do what? I have to add this one. And look, I can get from, and also I can get from here to, I can get from here to here from here. So I have to add this one. And what else can I do? I can get from here to here on here. So I have to add this one. See? So you can kind of see, it's kind of a visualizing how you can get there from, you know. And there's a direct, anytime you can get from one to another one through any kind of a circuitous path, there's a direct one there. See? That's a way to visualize. Now, what about this? What about D? What does the star mean? What in words? What was the star? Rho star is the what? Reflexive transitive closure. So that just combines both of them.
Yeah.
All right. So this one here, this one that we just did is the reflexive closure. What about the reflexive? Sorry, this one that we did is the transitive closure. So let's do the reflexive transitive closure.
Bring in the identity stuff.
Yeah, that's exactly right.
That's all we have to do?
Yes. To the transitive closure, right?
Yeah, the one that's already made.
So, yeah, the reflexive transitive closure.
So pred star
Yeah, so give it to me. So pred star,
equals 0, 1, 1, 2, 2, 3, 0, 2, 1,
hold on, 0, 2,
1, 3,
1, 3.
0, 3.
Now we need all the
Now we need
reflexive.
0, 0, 1, 1, 2, 2, 3.
I think we're good. All right? So that's the reflexive transitive closure. So we just union that, the transitive closure with the, all right? This actually, this union over I of all the rho to the I, this is actually 14.32c. There's an algorithm, it's called Warshall's algorithm. And you can actually program this union over I of rho to the I, because that rho, when you use rho, when you use the matrix representation of the relation with the ones and the zeros, you can actually write it, you can multiply. Anyway, there's an algorithm. There's an algorithm that implements definition C. So you can write a program to compute the closure, the transitive closure of a relation. If you store the relation in a matrix of ones and zeros, there's an algorithm called Warshall's algorithm that computes the transitive closure of that relation. And it's very straightforward, but we don't have time to go into it. But some compiler, it's like I said, the compiler construction theory uses that relation, or uses that closure. Now, the next big topic, and this is a biggie, is called equivalence relations. Now, this is all going to look familiar when we introduce it, because one of the big equivalence relations that we have used all throughout, starting from day one, is the equals relation. So equals is an example of an equivalence relation. So let's first of all define what is an equivalence relation. So 14.33. What does 14.33 say? It's a definition.
Pretty straightforward.
Yeah, if and only if. A relation is an equivalence relation, so equivalence relation is a relation that has the following three properties. Now, does this look familiar? RST, remember RIST? Yeah, Ristel. We had an extra L for equals.
What was
But that was for equals, because you know when we said you can substitute equals for equals,
that's what Bristol was?
and that's what and that was one of the properties of equals. Now, so an equivalence relation in general, not just for equals but for other relations, an equivalence relation is defined to be a relation that is reflexive, symmetric, and transitive, all three, right? Okay. So will we ever prove that an equivalence relation has to be reflexive, symmetric, and transitive?
Probably not.
No, because that's a definition, right? Like an axiom. Okay. Now, how about 14.34? That's another definition. It says, let rho be an equivalence relation on B. Right? Then, now we have this interesting notation. Square bracket, little b, close square bracket, subscript rho. That little symbol there stands for the equivalence class of B. And it is the subset of elements of big B that are equivalent to little b. So take a look at this definition. It says X is an element of the equivalence class B. By the way we're going to say this, over here, we're going to say X is an element of, and the way we say this is equivalence class B. All right. Equivales X rho B. X is related to B. All right. So we need an example here. And I'm just going to make up one. Okay. So 14.33 example. B is going to be the set 0, 1, 2, 3, 4. We could just as easily use letters here, but, you know, whatever. And here's going to be our row. Now, can you tell me right off the bat what elements have to be in row? Be
I don't remember what row is.
No. Rho is an example of an equivalence relation over B. But if this is going to be an equivalence relation, what's the very first thing that we had to know about equivalence relation? What are the letters? RST. What does R stand for? Reflexive. So if this relation is going to be reflexive, what does it have to have in it?
0, 0.
Yeah. Yeah. So is there, now do you see what I'm saying? This is,
3 times, right?
well, no. I'm defining rho. Okay. So it's going to be 0, 0, 1, 1, 2, 2, 3, 3. Okay? Oh, 4, 4.
Don't need to erase.
Okay? Now, I'm also telling you that there is a 0, 1 in here.
Why would you do that?
Well, I'm just to make it a non-trivial. I mean, we could just,
Symmetric.
but in order for it to be symmetric, if a 0, 1 is going to be in there, what also has to be in there? A 1, 0. Okay, and I'm also going to tell you that there's a 0, 3 in there,
Okay.
right? But if there's a 0, 3 in there, what do you know has to be in there? A 3, 0. Okay? And I'm also going to tell you that there is a 1, 3 in there. Okay? But if there's a 1, 3 in there, what else has to be in there? A 3, 1. Okay? And I'm also going to tell you that there's going to be a 2, 4 in there.
Okay.
Watch it.
4, 2.
So there's got to be a 4, 2. Now here's my question. We know that this is
It's already
reflexive, right?
Yeah.
We know it's symmetric. What about transitive?
It's not.
It's already transitive.
No, not anymore.
Yep.
Well, there's a 0, 1 and a 1, 0. There must be a what?
0, 0.
And there is. There's a 0, 3 and there's a 0, 3 and a what? 3, 1.
So
There's already a,
0, 1.
no.
Yeah.
Oh yeah, 0, 1. Yeah, right.
Trick.
Do you think do you think we're safe on the transitivity?
Yeah, we're actually good.
Yep.
Can you sort of run through the ones there? Yeah. All right. So I'm saying this is rho, right? Now,
Wait.
I'm saying, do you agree that this rho is an equivalence relation? It is an equivalence relation, right? Now let's go to 1434 definition. What are the elements that are in equivalence class 0? By the way, I'm just going to, sometimes we omit the row if we know what we're talking about here. Okay. So tell me, what elements, what does this, I want to know, what does this equal? Well, yeah, what does this equal? What is it? I mean, what does it mean? Yeah, my question is, what symbol do I write down here next?
Empty set.
What is an equivalence class? What is it? What kind of thing is it? What is its type? What is the type of an equivalence? What is here? Can you tell from this? What is this type?
Is it a relation?
Set.
Boolean?
Okay.
It's a, well, you're close. Okay, first of all, is it a set?
Guessing it's
Yeah.
not.
It's a subset.
So,
So that must be a set.
it's a subset. So it is a set. So are you agreed then that it's this? We got to start with this, right? Now, my next question is, you said a set of ordered pairs.
Probably not, I guess.
Well, what is it? What does it look like? What is it a subset of?
Set of relations?
Elements of B,
It says it's a set of elements of B.
which are ordered pairs.
No.
Whoa. Is B a set of ordered pairs?
Only over a relation. So it's just,
It's just a set.
It's a set of elements of B. It's a subset of these, right? So does everybody agree that what's going to go in here is either going to be a 0 or a 1 or a 2 or a 3 or a 4?
Right.
Now, which subset is it?
I have no idea.
Well, read. Come on. This is, the equivalence class of B is a subset that are equivalent under rho to B. It's the ones that are related to Z. It's the ones that are related to 0.
0, 0, 0,
So 0 is related to itself because we have a 0, 0.
Okay.
1 is related to it.
It's all of them.
3.
And 3. Now, is everybody, are you with me on this?
Yeah.
Okay. And now how about the equivalence class 1? What set is that?
1,
Yeah?
0, and 3.
Oh. What about equivalence class 2?
4. 2, 4.
2 and 4. What about equivalence class 3?
It's going to look a lot like equivalence class 4.
3 is related to itself.
0, 3, 3, 3.
0, 1.
1, 3.
Booyah.
And what about 4? Equivalence class 4.
2, 4.
2, 4.
Ha! And what do you notice about this, sports fans?
There's no pattern at all.
No pattern at all.
Well, no. I mean, you know that in the sets, order doesn't count, right? So what do you know about equivalence class 0 compared to equivalence class 1? They're the same. And what about equivalence class 0 compared to equivalence class 3? They're the same. And what about equivalence class 2 compared to equivalence class 4? They're the same. Okay, so
if you find 0, you know what the sets are for the rest of the elements of it.
yeah, yes. And what I'm saying, look, do you understand now that this set, and this set are 3 different names for the exact same set? Are you with me? These are 3 different names. All you have to do is put one of the elements in there, and that names that one. And you can put anyone in there to name it. You see what I mean? So now, check this out. Note the following also. Note this. Watch this. What about 0? What about equivalence class 0 intersection equivalence class 2?
Oh,
What's that?
Nada.
That's the empty set,
you said.
right? And what about, are you with me? And what about equivalence class 0
True.
union equivalence class 2? That's the whole universe of discourse that we're talking about, right? Are you with me? And so, you guys, 0, 2. Now, what is this a set of? What is this a set of? No, it's not a set of ordered pairs. What is it a set of?
Set of relations.
No. This equivalence class is not a relation.
It's a subset of elements of B.
No.
Equivalence class itself.
Yes. It's a set of sets, right? This is a set of sets. In fact, it is a what? It is a what? Starts with a P. I feel like Ferris Bueller's Day Off. No.
Partition.
It is a partition of B.
This is one of those things.
Now, throwback is exactly right. So now, do you remember what a partition is? Remember with the analogy we used for partition? We said it's like if we had this chairs in this room and we put down partition.
Oh, yeah.
Remember? And what did we say they were? They were pairwise.
Parts of
The union of all of them.
Parts of a whole.
Yeah, they were parts. And if you took the union of all of the sets, you got the whole thing.
The intersection is nothing.
The intersection of each pair was the empty set. So this is a partition. You understand that if I were to write this out, this would be brace, and then this would be brace 1, 2, 0, 1, 3, and then this would be brace 2, 4. Right? So this would be a set of sets. Right? And that's a partition. Okay? And what's interesting is this. This is quite an amazing thing when you think of it. There's a really cool structure to this. Discrete structure. This is a really nice discrete structure. anytime you have an equivalence relation, anytime you have an equivalence relation, that equivalence relation defines a partition of its elements. It partitions its elements into these sets, into these subsets, and these subsets are mutually, what am I trying to say? What's the word? The subsets are empty. The intersection is empty. Disjoint. Pairwise, yeah. That's, had a senior moment there. Yeah, they are pairwise disjoint, and their union is the entire set. And it's but why should it be that if it's reflexive, symmetric, Ristle, reflexive, symmetric, and transitive? If it's reflexive, symmetric, and transitive, it'll do this. And not only that, you can go the other way around. If you have a set of elements, you know, like B, so say you had 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or if you had A, B, C, D, E, F, G, H, I, J, K, if you partition those, put bunch in one partition, a bunch in another, a bunch in another, and such that they are pairwise disjoint, and the union is the whole thing, you can actually define an equivalence relation based on that partition. It goes both ways. Given a partition, there is an equivalence relation, and given an equivalence relation, there is a partition. So one of the key, that's a very basic property of discrete structures with relations that are equivalence relations. Okay, that was a good time to stop. Good place to quit. So we'll see you tomorrow, right?